Welcome to the deep dive. Today, we're going deep into operating
Oh,
systems,
yeah.
that software that most people don't even think about,
Right.
but that makes our digital world possible.
Yeah, the unsung heroes. Definitely.
And we've got some pretty interesting source material for this deep dive.
Who
Some
did?
technical excerpts. Looks like it might be from a textbook,
Mm,
and it looks like it's written in another language.
yeah, it does.
So it's a bit of a puzzle.
It's a puzzle, but that's why we're here,
And
right?
that's why we're here, yeah. So what's the mission for today? What are we hoping to figure out?
Well, I think first we need to translate some of this jargon,
Oh, yeah, definitely.
lay the foundation to, what is an operating system
Right,
and, how have they evolved to what they are today.
right.
But then we can get into the really cool stuff, like how a cache hit, can make your computer faster,
Okay.
or the crazy way that your CPU can juggle all these tasks seemingly at the same time.
All right, you've got my attention. Let's back up for a second. For those of us who aren't, computer science PhDs,
Sure.
what actually is an operating system?
At its core, it's the software that connects you, the user,
Okay.
to the hardware, the
Right.
physical components of your computer.
Right.
Without an operating system, all you have is a bunch of circuits that don't know what to do.
Right.
The operating system manages all the resources, the memory, the processing power,
Okay.
and lets you interact with the computer and run your applications.
So it's kind of like a conductor leading an orchestra.
Yeah, that's a good analogy. And what's interesting is how operating systems have evolved.
Yep.
Our source material here talks about how we went from simple batch processing where computers just crunch numbers, no human interaction,
Okay.
to the sophisticated interactive systems we have today.
Yeah, it's pretty amazing to think about, from number crunching machines to these multitasking marvels.
Yeah.
I mean, I'm using one right now to record this, but what about all the different operating systems that we have?
Right.
Windows, Mac OS, Linux. Do those differences really matter when we're talking about the fundamentals?
Well, they matter at the user interface level, sure.
Right.
But what we're talking about today are the underlying principles that are common to all operating systems.
Okay.
Think of it like human anatomy,
Okay.
Whether someone is tall or short, their heart and lungs work pretty much the same way.
Right.
And it's kind of the same with operating systems.
Okay.
If you understand the fundamentals, you can understand the workings of any OS.
All right, so let's get into those fundamentals then. Let's start with the hardware itself. Why is that physical architecture so important for the operating system?
Well, it's like the foundation of a house.
Yeah.
The hardware, specifically the CPU, the memory, and those input-output devices,
Right.
really dictate what the operating system can do
Okay.
and how well it can do it.
So let's start with the CPU, the brain of the computer. It basically executes instructions, the code that makes programs run.
That's the basic idea, yeah.
Okay.
But modern CPUs are way more sophisticated than that.
Okay.
They use techniques like pipelining, where they execute multiple instructions at the same time.
Oh, wow.
Kind of like an assembly line.
Oh, okay.
So while one instruction is being fetched,
Oh.
another one's being decoded, and another one's being executed.
So it's not just one at a time. It's like this constant flow.
Exactly. And then some CPUs, superscalar CPUs, can actually execute multiple instructions per clock cycle,
Oh,
which makes them even faster.
okay.
And our document really emphasizes this point that, understanding how the CPU works
Right.
is vital for designing efficient operating systems.
So the operating system has to be designed to take advantage of all those capabilities?
Absolutely. It's like writing a play for a specific actor.
Okay.
You need to know their strengths to get the best performance.
Right, okay. So then we've got the CPU, and then what about memory? That's like the computer's short-term recall, right?
Exactly. And there's this whole hierarchy.
Okay,
You've got registers that are on the CPU itself.
okay,
Super fast access.
okay.
Then you've got cache memory, then main memory, which is your RAM,
Right.
and then finally secondary storage, like your hard drive.
So it's like a whole range of memory, each with its own kind of speed limit and its own costs?
Yeah, precisely. And this is where that cache hit concept comes in.
Okay,
So when the CPU needs a piece of data,
okay,
it first checks the cache.
okay,
If it finds it there, boom, cache hit. Super fast.
okay,
But if it's not there, it has to go to main memory,
okay.
which is much slower.
Right.
And that can really impact performance.
So the operating system is trying to orchestrate things so that you get as many of those cache hits as possible.
Yes, exactly.
Hmm.
And our document goes into a lot of detail about how these cache lines, chunks of data
Okay.
that are transferred between the different levels of memory,
Okay.
are managed to make that happen.
To optimize that. Okay, so we've got CPU, we've got memory, and then what was that last part of the hardware puzzle?
Input-output devices.
Okay,
Those
right.
peripherals that let you interact with the computer.
Right, so keyboards, mouse, display, all that stuff.
Exactly. But the operating system needs a way to talk to these devices.
Okay,
And that's where device drivers come in.
okay,
They're like translators,
okay.
enabling the communication between the OS and the specific hardware.
So like different languages that need to be translated for them to talk to each other.
Exactly. And our document actually compares how different operating systems handle this.
Oh,
It gives the example of UNIX and Windows having different approaches.
oh, interesting. So different solutions to the same problem.
Exactly.
Yeah.
But one common technique is something called DMA, Direct Memory Access,
Okay.
which lets certain devices access main memory directly
Okay.
without having to go through the CPU.
So it frees up the CPU to do other stuff?
Exactly. It's all about maximizing efficiency.
Right. Okay. So we've laid this foundation now with the hardware. Now we can start to understand how the OS actually manages the programs we run,
Right.
which brings us to the concept of processes, right?
Exactly. Processes are basically instances of running programs.
Process. That sounds kind of jargony.
It is. Think of it this way.
Okay.
You have a recipe.
Okay.
That's your program file.
Okay.
But when you actually start cooking,
Yeah.
that's the process. You know,
Yeah.
all the ingredients and the steps and the actions all happening.
Okay, so like opening a web browser creates a process, and then opening a word processor creates another process, and so on.
Exactly. Now imagine this. You have one CPU,
Right.
and all these processes are competing for its attention.
Right.
That's where multitasking comes in.
Yeah, boy.
The operating system rapidly switches between all these different processes,
Okay.
giving each one a slice of CPU time.
Right.
It happens so fast that it seems like they're all running at the same time.
So it's like a chef juggling all these different dishes on the stove at the same time.
That's a good analogy.
Yeah.
But it takes a lot of coordination behind the scenes.
Right.
And our document goes into the components of a process.
Okay.
It has its address space, which is the portion of memory it uses.
Okay.
It has registers, which hold data the CPU needs.
Right.
And then the program counter keeps track of which instruction is being executed next.
So each process has its own little workspace that it's operating in.
Exactly. And the operating system keeps track of all of this with something called a process table.
Okay.
It's like a librarian keeping track of all the books that are checked out.
Right. Okay.
But here's where it gets even more complex.
Oh.
We have to talk about threads.
Threads. Another layer of complexity.
Think of threads as like mini processes within a process,
Okay.
allowing for even more fine-grained control over execution.
Oh, okay.
So for example, in a word processor, you might have one thread that's handling your typing, while another thread is doing spell checking in the background
Oh, okay.
at the same time.
So now it's not just processes competing for the CPU, it's threads within those processes.
Exactly. And modern CPUs with multiple cores
Right.
can actually run multiple threads simultaneously.
Oh, wow.
So the document hints at how operating system design has had to keep up with these advancements in hardware.
Right. Keep evolving to take advantage of that. Okay, so we've gone from a single CPU juggling processes to multiple cores juggling threads.
Well, a lot. Yeah.
This is definitely a deep dive. But before we go too far down that road, I do want to zoom out for a second.
Okay.
Because our document also talks about different types of operating systems.
Yeah,
So can we talk about those categories for a bit?
absolutely. It's interesting to see how the fundamentals we've talked about
Right.
play out in different ways depending on the OS's purpose.
Okay.
So, for example, you have batch systems,
Okay.
which were common in the early days of computing,
Right.
and they just process jobs in bulk, no user interaction.
Not exactly the interactive experience that we're used to.
Right. And that need for interactivity led to the development of time-sharing systems,
Okay.
which let multiple users interact with the computer seemingly at the same time,
Okay.
each getting a slice of that CPU time.
So like sharing a pie.
Exactly. Everyone gets a piece.
Right. From solo number crunching to sharing the pie.
Exactly. And then as computers became more powerful and interconnected,
Right.
we saw the rise of distributed systems,
Okay.
where the computation is spread across multiple machines.
So like a team effort.
Yeah, teamwork for computers.
Okay. And then, of course, we have the operating systems that are in, all these devices that we use every day.
Right.
Smartphones, controllers, all of that. Embedded systems.
Exactly. Those are specialized operating systems.
Right.
They have to be very lightweight, very efficient, and often they're designed for a specific task.
Okay, so it's not one size fits all for operating system?
No, not at all.
And then what about real-time systems? Those sound pretty intense.
They are. These are systems where timing is critical.
Okay.
Think industrial control.
Okay.
Robotics, medical devices.
Got it.
They have to guarantee a response within a specific time frame no matter what.
Oh, wow.
So it's a very different set of constraints.
Right. So from managing our documents to controlling critical infrastructure, operating systems really are kind of the unsung heroes of the digital world.
I think so. And this variety of OS types just shows how many different tasks computers perform today.
Right. And all of them enabled by the operating system.
Exactly.
Well, we've covered a lot of ground in this first part of our deep dive.
We have?
We've gone from, just a basic definition of what an operating system is
Right.
to exploring the hardware that it runs on,
Yeah.
the processes and threads that it manages, and
Mhm.
even the different types of operating systems out there.
It's a lot to take in.
It is a lot to take in, but it's a good foundation for our next dive,
Definitely.
where we'll uncover even more secrets about how operating systems work.
Absolutely. We'll get into how they manage resources,
Okay.
ensure security,
Right.
and even how they might shape the future of computing.
All right. Well, I am definitely looking forward to that. So to all our listeners out there, stay tuned for part 2 of our deep dive into operating systems.
We'll be right back.
Welcome back to the deep dive. I'm still trying to wrap my head around all those hardware details from our last segment.
Yeah, it's a lot.
CPUs, memory hierarchies, all of that. It's just amazing how complex it all is.
It is. But remember that all that hardware is just the stage.
Okay.
Now we get to see how the operating system directs the show.
Right.
Managing all those resources, making sure everything runs smoothly.
And we left off talking about processes and threads.
Right.
And I remember you mentioned something about a process table that the OS uses.
Yeah, exactly. That's like the OS's master schedule.
Okay.
It determines which process gets access to the CPU and when.
So it's like a traffic cop directing traffic.
Kind of, yeah. But it's not just a simple first-come, first-served situation. There are all these sophisticated scheduling algorithms that the OS uses.
Right, to optimize things.
Exactly. To make the most efficient use of the CPU's time.
So some algorithms might prioritize processes that need quick bursts of processing.
Exactly. While others might favor longer, uninterrupted tasks.
Okay, so different strategies for different situations.
Right. Our document actually names a few classic examples.
Okay, what are those?
Like first come, first served, shortest job first, round robin.
Okay, so first come, first served is like, a line at the bakery.
Yeah.
And shortest job first is like prioritizing the quick orders.
Exactly.
And round robin is like making sure everyone gets a turn.
You got it.
Yeah.
But it can get even more complex than that.
Oh, boy.
Some algorithms take into account things like the priority level of a process
Okay.
or any deadlines it might have,
Oh, wow.
even how long it's been waiting already.
It's like this constant balancing act.
It is a never-ending game of Tetris, trying to fit all these pieces together.
That's a great analogy. So all of that is just about the CPU.
Right. But there are other resources that the OS has to manage as well.
Absolutely. We're talking about memory, I/O devices, storage space, network connections, everything.
It's a lot to keep track of.
It is. The operating system is like a conductor, orchestrating all of these resources.
Okay, so it's about more than just keeping things fair. It's about making sure everything runs smoothly.
Exactly. Preventing conflicts, allocating resources efficiently. It's a big job.
So how does the OS actually control access to all these resources? It can't just be a free-for-all, right?
You're right, it can't. That's where synchronization comes in.
Synchronization.
Yeah, it's all about coordinating the actions of multiple processes
Okay.
to prevent conflicts and make sure the data stays consistent.
So it's like, I don't know, dancers moving in perfect harmony,
Yeah,
making sure no one steps on anyone's toes.
exactly. Imagine if you had two processes trying to write to the same file at the same time.
Oh, that would be bad.
It would be chaos. So you have these synchronization mechanisms like mutexes and semaphores. Okay, mutexes and semaphores.
Yeah, they sound technical,
They do.
but the idea is pretty simple. They act like locks,
Okay.
making sure that only one process can access a shared resource at a time.
So like a traffic light, controlling the flow of processes.
Exactly, preventing collisions.
So if one process is writing to a file, other processes have to wait their turn.
Right, to make sure the data doesn't get corrupted.
Okay, that makes sense. And are these mutexes and semaphores used everywhere?
They're crucial for all sorts of things.
Okay.
Database management, multi-threaded programming.
Right, because we talked about threads earlier.
Yeah, now you have multiple threads within a process and multiple processes,
Wow.
all potentially trying to access the same resources.
It's a lot to keep straight.
It is.
Yeah.
It adds another layer of complexity to the whole synchronization challenge.
Right, so you need even more sophisticated techniques to manage that.
You do. Things like condition variables and monitors.
Yeah.
Our document just mentions those briefly, but it shows how multi-threading really ups the ante for the operating system.
Okay, so we're starting to see why operating systems are considered such complex beasts.
They are. But there's also a certain beauty to it. This intricate dance of processes and threads and resources.
It's like a well-conducted orchestra.
Exactly. Everything working together in harmony.
Right. Speaking of well-organized things, we touched on memory management earlier,
Right.
but we didn't really get into the details.
We didn't. And it's a crucial aspect of what the OS does.
So how does the OS handle memory management?
Well, remember that hierarchy of registers, cache, and main memory we talked about?
Yeah.
It's more than just that.
Okay.
The OS has to decide which process gets which portion of memory,
Okay.
make sure they stay within their allocated space,
Right.
and protect their data from other processes.
So it's like a landlord managing an apartment building, making
Yeah.
sure each tenant has their own apartment.
Exactly. And making sure no one's breaking down walls to get into their neighbor's place.
Yeah, right. So it's about organization and security.
Absolutely. And one common technique that operating systems use is called virtual memory.
Okay, virtual memory, what's that?
It's a way to create the illusion that each process has its own dedicated memory space,
Okay.
even if the physical memory is shared.
Oh, so it's like a magic trick.
In a way, yeah.
Yeah.
The OS swaps chunks of data between main memory and secondary storage,
Okay.
so it's seamless to the user.
So even if my computer only has a limited amount of RAM, virtual memory can make it seem like I have more.
Exactly. It's another way the OS abstracts away the complexity of the hardware.
Right, it makes things easier for us.
Right. More user-friendly and more efficient.
Okay, that's pretty cool. Are there other memory management tricks that the OS has up its sleeve?
Oh, there are a bunch. Our document mentions paging and segmentation.
Paging and segmentation, those sound familiar.
There are two common strategies for dividing up the memory.
Okay.
Paging divides it into fixed-size blocks called pages, while segmentation divides it into variable-size blocks based on the logical units of a program.
So it's like slicing a cake into equal pieces versus cutting it based on the layers and fillings.
That's another great analogy.
Hmm.
And each approach has its pros and cons, depending on the situation.
Right, so the OS has to choose the right tool for the job.
Exactly. But the main goal is always to make efficient use of the available memory.
So I'm sensing a pattern here.
Oh, yeah.
It seems like OS design is all about finding the right balance
That's right.
between efficiency and flexibility, speed and security, providing access, but also protecting resources.
You're absolutely right. It's a constant juggling act.
And that brings us to another important aspect of memory management, protection.
Right. The OS has to make sure that processes can't access each other's memory.
Okay, yeah, because if one program could just peek into another program's memory,
Right.
that could be really bad.
It would be. It could steal data, crash the system, all sorts of nasty things.
Right, so how does the OS prevent that?
It uses a variety of mechanisms, both hardware and software,
Okay.
to enforce these memory boundaries,
Okay.
basically creating isolated sandboxes for each process.
Sandboxes, like those play areas where kids can build sandcastles without messing up the rest of the park.
Exactly. Each process gets its own protected space to play in,
Okay.
without interfering with other processes or the operating system itself.
These analogies are really helpful, I have to say.
Glad to hear it.
It's like you're translating the secret language of operating systems.
Oh, I'm trying. So now that we've talked about memory management,
Okay.
let's move on to another crucial component, file systems.
File systems, those are how files are organized on our hard drives, right?
That's the basic idea, yeah.
You know, folders, files, all that.
But it's actually a lot more than that.
Okay.
File systems define how data is stored, accessed, and managed on a storage device.
So they're like the librarian of the computer.
Yeah.
Uh,
Keeping track of all your documents, images, videos, programs, everything.
Okay, so instead of just having this jumbled mess of data on the disk,
Right?
the file system creates order and structure.
Exactly. It makes it possible to find and manage your files.
And I'm guessing there are different types of file systems.
You guess right. Just like there are different types of libraries.
Okay.
Different file systems have different strengths and weaknesses.
Right, so some might prioritize speed, others reliability, others security.
Exactly.
Okay, so what are some examples of these different file systems?
Well, you might have heard of FAT, NTFS, XT4.
I think I've heard of NTFS.
Yeah. That's the standard for modern Windows systems.
Okay.
FAT was more common in older Windows versions,
Okay.
and XT4 is often used with Linux.
Okay, so again, not a one-size-fits-all situation.
Right. It depends on the operating system, the storage device, and the user's needs.
So the OS has to choose the right file system for the job.
Exactly. But no matter what file system is being used, the OS provides a layer of abstraction. So users and programs don't have to worry about the low-level details of how data is physically stored.
Right. It simplifies things for us.
It does. You can just use simple commands like open, read, write, close.
Right. So it's like having a personal assistant who handles all this tedious detail.
I like that analogy. And these file system commands are just one example of the many services that operating systems provide.
Services? Like what else?
Everything. Managing network connections, handling user authentication, providing a platform for running applications.
Okay, so it's like a one-stop shop for all our computing needs.
Exactly. The OS creates a stable, secure, and efficient environment for everything we do.
It's pretty amazing when you think about all that goes on behind the scenes.
It is. We've gone from the hardware to processes, memory management, file systems, and now services.
It's like peeling back the layers of an onion, revealing more and more complexity with each layer.
I like that analogy. But with all this talk about complexity and resources, we can't forget about one of the most important aspects of operating systems: security.
Right. Because with all the cyber attacks and data breaches these days,
Yes.
security is top of mind for everyone.
Absolutely. And that's a perfect segue into our next segment,
Okay.
where we'll explore how operating systems act as guardians of our digital lives.
Welcome back to the deep dive. We've really gone deep, haven't we?
We have.
Into the inner workings of operating systems,
Right.
all the hardware they manage,
Yeah.
those complex tasks they have to handle, processes, memory, files, everything.
It's a complex ecosystem for sure.
It is. But all this complexity is there for a reason, right?
It is.
It's to create the stable and efficient and secure platform for everything we do digitally.
Absolutely. And that brings us to this very important question
Okay,
of security.
right.
How do operating systems keep our data safe?
Yeah, because these days, with all the cyber attacks and data breaches,
Right.
security is a huge concern.
It is a huge concern. And operating systems are right there on the front lines.
Okay.
They use this multi-layered approach,
Okay.
using both hardware and software
Right.
to protect our data.
Okay. So it's not just one thing, it's a whole bunch of techniques working together.
Exactly. And one key element is access control.
Oh, okay. Access control. What is that?
It determines who can access what data and what they can do with it.
Okay.
It's like different levels of security clearance.
Okay.
Some users might have read-only access to certain files.
Right.
Others have full read-write access.
Okay.
And some might be completely locked out.
So it's like different locks and keys for different rooms.
Exactly. Operating systems use these things like user accounts,
Okay.
groups, and permissions
Yeah.
to create this fine-grained control.
Okay.
Every time you log in,
Right.
you're being granted access to a specific set of resources
Right. Based on who you are.
based on your credentials. Exactly.
Okay. Access control makes sense. What else is there? Right. Encryption. That's important too.
It is. Encryption transforms data into this unreadable format.
Okay.
So it's basically gibberish to anyone who doesn't have the key.
So like a secret code.
Exactly.
Mm.
And it protects sensitive information both while it's being transmitted
Okay.
and also when it's just stored on your device.
So like when I buy something online, my credit card details are encrypted so hackers can't steal them.
Exactly. Encryption is super important in our increasingly interconnected world.
It is, yeah. What about firewalls? I know those are important for security too.
They are essential. Firewalls are like gatekeepers, controlling the flow of network traffic in and out of your computer.
Okay.
They can block malicious connections, prevent unauthorized access.
They're like security guards at the entrance to a building.
Exactly. Checking everyone's ID, making sure only authorized people can get through.
Okay, and do operating systems have firewalls built in?
Most modern operating systems do, yes.
Okay, so you can customize your security settings based on your needs.
Exactly. It gives you control over how much protection you want.
Right, okay. So we've got access control, encryption, firewalls. It sounds like this whole multi-layered defense system.
It is, and that layered approach is really important because,
Yeah.
the security landscape is constantly changing.
Right.
New threats are emerging all the time.
Okay.
So operating systems need to be constantly updated, patched.
To stay ahead of the bad guys.
Exactly. It's like a never-ending arms race.
Yeah, it is. But it's good to know that there are people working hard to make operating systems more secure.
Absolutely. There are some brilliant minds dedicated to protecting our digital lives.
That is good to know. Well, speaking of brilliant minds,
Yeah?
what does the future hold for operating systems? Are there any new trends that are going to shape how they evolve?
That's a great question. And our source material does touch on a few interesting possibilities.
Okay, like what?
One clear trend is the growing importance of virtualization.
Virtualization. Is that like virtual reality? I'm picturing people wearing headsets interacting with operating systems in a virtual world.
Not quite. Virtualization is about running multiple operating systems on a single physical machine.
Wait, multiple operating systems on one computer, how does that even work?
It involves creating these isolated environments called virtual machines
Okay.
that mimic the behavior of a real computer.
Okay.
So each virtual machine can run its own operating system
Okay.
and its own applications completely independently.
Wow, so it's like having multiple computers all running inside one physical computer.
Exactly. It has a bunch of advantages.
Okay, like what?
It lets you maximize resource utilization
Okay.
because you can run multiple workloads on one machine.
Okay.
It enhances security because each virtual machine is isolated.
Right.
So if one is compromised, the others are still safe.
Okay.
And it also makes software testing and deployment a lot easier.
So instead of having a separate physical server for each application, a company could run multiple virtual servers on one powerful machine.
Exactly. It's a game changer for data centers and cloud computing.
That makes sense. Okay, virtualization sounds like a big deal. What else is shaping the future of operating systems?
Another big one is the continued rise of mobile and embedded systems.
Right. Smartphones, tablets, all those devices we use all the time.
Exactly. And those require specialized operating systems
Okay.
that are lightweight and energy efficient.
Right, because those devices have limited resources.
You do. They have to do more with less.
Okay, that's interesting. What about AI?
AI.
Yeah, artificial intelligence. Everyone's talking about how it's going to change everything. Will operating systems be impacted too?
Oh, absolutely. Artificial intelligence requires a lot of computing power.
Okay.
Huge data sets, complex algorithms, specialized hardware.
Right.
Operating systems are going to play a key role in managing all of that.
So we might see operating systems that are specifically designed for AI.
It's definitely possible. The future of operating systems is very much tied to the future of AI.
That's really fascinating. It sounds like we're entering this new era of computing, and operating systems are evolving to keep up.
I think so. It's an exciting time to be following this field.
It is. This deep dive has been incredible. We've really explored the hidden depths of operating system.
We have, from the hardware all the way to the future of computing.
It's amazing to me that we've created these complex systems that, despite all the complexity,
Yeah.
often just work seamlessly in the background.
Right, we don't even think about them.
We don't. But
Yeah.
they're there powering everything we do on our computers and our devices.
They're the unsung heroes for sure.
They are. So to all our listeners out there, next time you use your computer or your smartphone,
Yeah.
take a moment to appreciate the amazing engineering that is the operating system.
It's a symphony of software and hardware working together to make our digital lives possible.
It is. Thanks for joining us on the deep dive.
Thanks for listening.